Assalamualaikum. I am Muhammad Rakibul Hassan presenting our paper Investigation of the Effect of MFCC Variation on the Convolutional Neural Network Based Speech Classification in this conference 2020 IEEE Region 10 Symposium at Dhaka, Bangladesh. Another author of this article is Muhammad Mahbub Hassan sir. We are from Khulna University of Engineering and Technology, Khulna, Bangladesh. So let me mention the outlines of my presentation. Starting from relevant theories, I will describe the materials and methodology used in this work. Then I will describe what we have found in this work, and then our contribution, and then finally there will be a question and answer session. So please save your question for the end of this presentation. So what is speech actually? I can say speech are sounds that are filtered by shape of our vocal tract, including tongue, teeth, mouth, etc. And for each individual sounds or speech, I can say there will be different shape, and this shape determine what sound comes out. And vocal tract dynamics respond differently when speaking vowels or words. So what does that mean? For example, I am saying a vowel or, and again I am saying a word like bottle. So when I am saying a word like bottle, my tongue may touch my teeth, or I can say there is different sense in my vocal tract. But when I speak a vowel like it's quite kept fixed. So I can say vocal tract dynamics respond differently. I can say this is the core ideas of our work. So next, creation of dataset. As we are talking about convolutional neural network based speech recognition system, that's why dataset is an important task. For this work, we have chosen 7 isolated vowels here and 7 isolated words. The reason behind choosing these particular words are they are more prone to vary when spoken by different speakers. For example, Mr. X is saying this word as bottle. Again, Mr. Y is saying these words as bottle. So they can vary, and we are working with variation. So this is the process. At first, we have recorded continuous stream by smartphone. The recorded was stereo track. Then we have converted stereo track to mono channel. At the time of recording by smartphone, we have recorded as a continuous stream. For example, bottle, bone, copy, dokan, and a little silence in between them. So we need to clip into distinct speech token. By clipping, we can found bottle at a different data and bone as a different data. By this process, we have found 40 data in each of the speech class. And next, feature extraction. We can't feed the audio data directly to neural network model. We need features, and for this particular work, we have chosen male frequency capital coefficient here, which is called MFCC, and to extract this, we have used Librosa Python package. Next, convolutional neural network model. To code this, we have used Python 3.5 on Jupyter Network as our environment, and we have used Keras open source neural network library. And to determine the recognition performance, we have chosen this particular 4 metrics: loss, accuracy, confusion matrix, and cross-validation score. We will come later on by one. So this is the recognition model architecture. This is the architecture we have used in our work. Here the input shape is 20 by 13. 20 means number of MFCC sample and 13 means number of time sample. At the beginning we have a convolutional layer. Convolutional layer performs convolution operator to its input, and here a kernel or feature here is shown. It passes to its input feature and produce subsequent feature maps according to this formula. And typically after a convolution layer there will be max pooling to reduce the feature size. Here 19 by 10 is reduced to 9 into 5, and there will be dropout layer as a measure of weight regularization. And again here we have 2 dense layer optimization, and at the end there will be output, and our output have 7 different classes. That's why shape is 1 into 7. And typically a convolutional neural network model has one or many convolution layer at the input side and one or many dense layer optimization at the output side. We have used one convolutional layer here and 2 dense layer optimization here, and convolutional layer performs operation on 3 dimension data, whereas dense layer performs operation on one dimension data. To convert this 3 dimension data to this one dimension data, we have a flattening layer here. Now performance comparison between vowel and word recognition. Our first matrix was loss. So here blue line denotes the word and red line denotes the vowel. From this figure we can say that the vowel loss is less as compared to word loss. Again, from this accuracy comparison we can say this vowel accuracy, this red line, is greater than word accuracy. So from these two figures we can say that vowel recognition is better than word recognition. As for loss, vowel loss is less, and as for accuracy, vowel accuracy is higher. Next, confusion matrix. So what is a confusion matrix actually? I can say confusion matrix is a tool to measure the performance of a classification problem, and we are talking about classification problem. That's why confusion matrix is an important tool. So here 0.88 means that 88% cases O is recognized as O, and 12% cases O is recognized as A. So this O creates a little confusion in the whole vowel recognition scenario, and for other vowels this is, I can say, they're quite good because 100% cases they are correct prediction. For example, A is predicted A for 100% cases. But for word recognition performance, we can say there are a lot of confusion. For example, this particular word bone, 73% cases bone is predicted as bone, but for 18% cases bone is predicted as dokan, and for 9% cases bone is predicted bottle. Similarly, this particular dokan word also creates confusion. So I can say that vowel recognition creates less confusion as compared to word recognition. That in turn say that vowel recognition is superior than word recognition. Now k-fold cross validation result. Here k equal to 4. That means whole dataset is divided into 4 equal sections, and for each time 3 section has used to train the model and the rest section is used to validate or test the model. That's why we have here 4 types of validation accuracy, as 4 section has used to test the model at 4 different times, and the overall accuracy determines the average accuracy of these 4 types of testing. And here the overall accuracy of vowel recognition is found better than overall accuracy of word recognition. So vowel recognition outperforms word recognition in all 4 cases: loss, accuracy, confusion matrix, and cross validation score. Now what's the reason behind this performance deviation? If we notice the MFCC variation of vowel and word, we may find the answer. Say here the MFCC variation for vowel, we see that the MFCC does not vary so much as compared to word. Here word MFCC varied so much, here we can see. So MFCC of word has varied so much as compared to MFCC for vowel. This can also be proved from the wave shape. Here the wave shape of a vowel depicts that it is quite continuous. But for both word there is a silence or discontinuity within the wave shape, and this discontinuity created from the vocal tract variation. Also we can say this discontinuity resulted the variation of MFCC. So I can say variation of vocal tract dynamics is the answer. Now the contributions and conclusions. At first we have created the data set, we have collected raw speech data and then make them isolated, and then we have done some feature engineering, some statistical processing to find the variation among MFCC, and then we have created the neural network model, and there are optimum selection of the hyperparameters such as filter size, number of layers, etc. And finally, there are performance evaluation. For 4 different performance metrics, we have compared between vowel and word recognition, and we have found that performance is inversely proportional to variation. And finally, the question and answer session. Thanks a lot for your precious time. Any question is warmly welcome.